So today I'm going to talk about this quantum computing for multiscale PDE, but actually there's you will only say the multiscale PDEs in the end. So, yeah. So this is joint work with Junpeng, and he's a joint student with Shi Jin. So, well, he's the main driving force in this work, all this work. And Shi Jin, of course, I think all of you know. And also Nana Liu, she's a physicist. So we have a physicist here. Okay. And so that's I will introduce these three works. Okay. Well, so this it starts with so for most people it starts with Richard Feynman, and Richard Feynman gives this very famous quote, and he says, "Nature isn't classical, and you want to make a simulation of nature, you better make it quantum mechanical." But it's not easy. Okay, so even at that time he knows it's not that easy, and also he gave this speech at this conference in 1981. And as always, there is also some Soviet scientists also already gave this concept of quantum computing in his book, computable and uncomputable. So the famous year. Okay, Yuri Manning. I think he also was the director of the Max Planck Institute in Bonn for some time in 1990s. Okay, so it's not easy. So John Preskill in 2012, and he see is controlling large-scale quantum systems really, really hard, or is it ridiculously hard? It's impossible. Okay, so but despite his comment, so what is the current status? So this is a code atom array in Harvard in logging group, and they have managed to get like thousands or several thousands of qubits. So that's so they can already get that level, and they want this to be like 10,000 qubits. And if you get that, of course there is still the problem of error correction. But even with error correction, so they hope in the 5 years, and you can get like 50 logic qubits. Okay, so something like that in that level. Okay, and this is so I try to find this is this German quantum computing center, and they try to design all these kinds of quantum computers. And this is IBM superconducting quantum computer, because there are different technical routes for implement quantum computer. So this is a superconducting, and so this is in China, so in USTC, and this is optical quantum computer. And so both of them can achieve some kind of quantum supremacy. Basically, that means it is already outperformed the classical computer, but for some specific task. Okay, so that's what we know for the current hardware. So what about how to design the quantum algorithm? So before that, I have to introduce some basic stuff, because I guess many audience in this room, so they're not expert in that, right? So okay, so let's start from the basic concept. Okay, so this quantum state, or we say that qubit. Okay, so this is discrete quantum computing in some sense. There is also continuous quantum computing or analog quantum computing. So for the discrete quantum computing, so there's quantum state or qubit. So what is state space? State space is just simple. It's just a vector space. It's complex vector space. Okay. And with inner product, so that's a Hilbert space. Okay, so that's simple. And if it's finite dimensional, so this H would be the complex C to the power n. Okay, and for each qubit it's C2, and you have a tensor product of this n, small n qubits. So this n is the number of qubits, so that's a small n here. And capital N is 2 to the power n. So basically, it's increased a lot, exponentially increased with respect to the number of qubits. And so you can write a quantum state as a vector. So this vector is just capital N. So this the size is capital N, and you can have this Hermitian conjugate. But for physicists, they prefer to write this so-called Dirac notation. Okay, so this is this bra or cat. Okay, so this cat is just this vector. Okay, and the bra is conjugate. Okay, so that's it. Yeah. And if you want to write the inner product, of course, for mathematicians, we just write the curved bracket with psi and phi. But for physicists, we prefer to write this bracket. Okay, psi and phi, this is inner product. And if you want to write the outer product, it's also easy. So that's outer product, and that's a matrix. Okay, so this direct notation is nothing. Okay, and it's just another way of writing it. And all the quantum states are assumed to be normalized. So if you multiply a constant to a state, it remains the same. So we assume it's normalized. Okay, so the norm of psi is 1. Okay, and for the single qubit, if you write this down for a single qubit, it's you can just write a single qubit as psi equal to. So there are 2 bases, and so this A and B are complex number. Okay, and this basis, because it's C2, so it's just this 1, 0, and 0, 1. Okay, A, B are complex number, and it's normalized. So A squared plus B squared 1. Okay, so that's just a single qubit. And if you work hard a little bit, and you will know a single qubit can correspond to a sphere. Okay, it's all points on the sphere. And so that single qubit can also be notated as a Bloch sphere. Okay, so this is so you know that a single qubit can encode information on the sphere, and it's continuous. So it encodes a lot more information than a bit, right, in the classical computer. For a bit, it's just 0 and 1. Okay. Okay, so with this quantum states, and we want to do operations on the states, right? And because the states are normalized, so all the operations can only be unitary. Okay, because it has to preserve the norm of this quantum state, right? So the state is 1. The norm of the state is 1. So all this x, y, z are polygates, and they are unitary matrix. It's 2 by 2 unitary matrix because it's operating on C2. And so this, what is the operation? What is the effect of operating x? So for example, if we have x and acting on 0, because x is just 0, 1, 1, 0. So x acting on 0 would be 1. Okay? And x acting on 1 is 0. So x is just a flip, right? It flips between 1 and 0. And there's another important gate. It's the Hadamard gate. Okay? And if you apply h on 0 and apply this, and you will get this will be just square root 2 of 0 and 1. So if you measure these states, it has a half probability to be at 1, 0, and half probability at 1. Okay? And also, so if you apply this, 1 over square root 2, 0, minus 1. Okay? So that's what you get for this h, and it's very important. So this Hadamard is named after the French mathematician Hadamard. And there's also the Phys gate, so there's this I, and of course there's exponential I pi over 4, and there is, in general, it could be exponential I zeta. And also there is this C0, so this is a 4 by 4 matrix. So 4 by 4 matrix is acting on 2 qubit, okay, because it's 4 by 4. So it's acting on 2 qubits. So there is some way, because if you it's very easily, so this dimension of matrix increase very fast. So there is a way to write down these matrices, and it's called quantum circuits. So if it's a Hadamard gate, okay, it's this one, and you just write an H and a box, okay. And before that is input state, and after that is output state, okay. And this is C0 gate, okay, C0 gate. And what is effect of the C0 gate. So it defines a controlled operation. It defines a controlled operation. So if you use C0 gate to acting on some, so that there is this is 2 qubits. So suppose the first qubit is 0, and you say that the output, so here is 0. It's just does not change. So this A plus B is just A plus B or 2. Okay. So if this is A is 0, so this output on the B register does not change. If BA is 1, so it becomes A plus 1 or 2. Okay? So that it will change, that will flip, right? Okay, so this C0 gate, it carries out a controlled operation. So this is called controlled NOT. It's like if else in the classical computing, right? Okay. And so this C0 gate can carry out that. And in general, so if you have an input, it's psi, and you have U1, U2, UK, and so you have all these unitary operations, and in the end, you have output, and you can measure it. Okay. And okay, so we have this series of unitary operations, and so we can just imagine we have an initial quantum state is psi 0, and it evolves, let's say, in time or in discrete time, and so we have a series of quantum states. So this is psi t, and we can define the quantum evolution operator. And of course, the most well-known quantum evolution operator is defined by this Schrödinger equation, right? Okay, and what is the Schrödinger equation? So we have this time independent. So by the time we assume this is time independent, Hamiltonian H. In general, this H can be a Hermitian operator or a Hermitian matrix. Okay, and so this satisfies this Schrödinger equation. So it's defined here, and the time derivative of this quantum state is times I equals to the H acting on psi. So now for this thing, the time evolution operator would be exponential minus I times ht, right? And if this is time dependent, it would be much complicated. Okay, and okay, in the end we have to do some quantum measurement. Okay, so how to do the quantum measurement? So in the easiest setting, in the finite dimensional setting, so it corresponds to some observable. So the observable corresponds to this Hermitian matrix, and we can because it's a Hermitian matrix, and we can do some spectral decomposition. And so when this quantum state is measured by this M, okay, and the outcome is a probability is random. Okay, so it becomes lambda is an eigenvalue, and P, this capital P, is a projection operator corresponds to the eigenvectors. And so this outcome will be lambda m, and with this probability Pm. Okay. I probably write this should be Pm. This is not m. Sorry. Yeah, this is here. Okay. So we can write down the expectation of the measurement, and this so we can measure several times, many times, and we can so because the outcome is random, we can have this expectation. Okay, so now we can talk about some basic algorithm. So the quantum computing is very different from the classical computing in some sense. For example, in the classical computing, usually you can copy. So very often you just copy V equals A, something like that. But in quantum computing, you don't have that. Okay, there's no unitary operation carries out the copy operation and also the delete operation. Okay, so there are some consequences for that. Okay, and now we just see some basic algorithms. So one of them is amplitude amplification. So basically you can prepare, usually you can prepare this kind of things. So this is a target, this is the state you want. Okay, but when you initialize, the weight of this target state is very small. So this P0 is very small. This Q0 corresponds to the probability of this state. And so this probability is very small. And the other things, and this side orthogonal, you can see this is just the orthogonal state. Okay. So what do you do? So there is this so-called Grover algorithm and then Grover rotation. So you can just use some trick. It's called Phys kickback. So you just express this p0 as some angle theta. Okay. And you can design this rotation operator and to make this rotation, and finally you want this the whole state. So each time and you rotate this angle, and in the end this angle will become, so in the beginning it's very small, but in the end it's close to 1. Okay, so in the end you have omega 1 probability to achieve this state. Okay, so that's the Grover's algorithm. So that's a very common sub-algorithm into quantum computing, and another one is quantum phase estimation. So that is U is a unitary operator and psi is an eigenvector. And U psi equal to, because this is a unitary operator, so the eigenvalue would be norm is 1. So this is exponential I 2 pi phi, and you want to find this phi. Okay, if this classical is very easy, you just divide, right? You multiply U psi by U, and you just divide by psi. But in quantum, it's not that straightforward. But this is very useful. For example, if you want to find the ground state, and if you design the HHL, this first linear solver, and it's all used this quantum phase estimation. So I will just show you how to do this with Hadamard test. Okay. So because this is very easy, this is a very simple algorithm, this circuit or algorithm. Okay. So let's psi be the eigenfunction. At U, this is the operator. Okay. And this circuit is like that. This is a 0 qubit, and this is psi qubit. Okay. Okay. And so this is Hadamard gate. You remember this for Hadamard gate. So H acting on 0, and you get square root 1 over square root 2, 0 plus 1, and if acting on 1, and you get this. Okay. So first, so we acting H on 0, and you get this square root 2, 0 plus 1. So this is a combination of these two. Okay, and psi remains unchanged. And then you have this called control U. So that means if this is 0, we do nothing. If this is 1, and we multiply psi by U. Okay, so this is control U operation, and this is 1 over square root 2. So because this is linear, so that's all the quantum computing are linear. So we just do this linear. And this is 0, and the psi, because this the first is 0, and this is 1, so we do the U operation. Okay, and then so we do this H again. We do H again, and so you get this 0 is 1 over 2. So you H multiplied by 0, and you get something. This is 0 plus 1 psi. So we switched to different parts. And if this is 1, this is the 0 U minus 1 U. Okay. So that's just some linear algebra. Okay. And you'll find this because we put 0 here because we want to find this probability. Okay. So we want to measure this qubit, and we want to find the probability of this qubit to be 0. Okay. We will measure the 0 state at qubit 0. And this P0 is nothing but the norm of this vector. Okay? The norm of this vector. The norm of this psi plus U psi. The norm of this vector. And if you calculate it, so this is just 1/2, 1 plus the real part of this thing. This thing is what we want, right? This thing is what we want. And this is, this psi U psi is exponential I r pi 2 pi phi, and the real part is cosine 2 pi phi. Okay, so from here, and you can know the probability, and you measure many times, and that's like a Monte Carlo, and you want to find the approximation of P0, and then you can find phi. Okay, so this is just how the quantum algorithm is working. So for this simple algorithm. Okay, And why do we do? If we just do this simple problem, it's nothing. Yeah. Why do we do this? Because, for example, this is a circuit for the quantum Fourier transform. Okay, this quantum Fourier transform is a unitary operator. Okay, you can see this is a unitary operator. It transforms the basis of this complex vector space to an orthogonal space. Okay, and also if this is some vector, you can say that it also transforms the coefficients of this vector to the new coefficient, and the new coefficient is a discrete Fourier transform. Okay, so when you apply this quantum Fourier transform, so that's the number of gates you get. So for the first line, there are n gates, and the second is n minus 1, so that's 1, and together it is n squared. Okay, so the gate complexity of QFT is n squared. Okay, but the classical complexity of FFT, of course, we know that this is 2 to the power n. This is capital N. Okay, so that's why we say that this has a small exponential speed up. Okay, and there are also some other exponential speed up examples, like quantum walk, like simulating sparse Hamiltonian. That's why it's very related to our talk, and also the spectrum. That's what Professor Enquist said. That's Shaw algorithm. Yeah. They use the QFT, this quantum Fourier transform, is a core part in this spectrum. Okay. That's why they achieve this speed up. But not all the problems can have this exponential speed up. For example, the search problem does not provide exponential speed up. So it only have a square root speed up. Okay. Okay. So let's talk about this Hamiltonian simulation. So because we know that quantum computer is based on quantum mechanics, and so the evolutions on the quantum computer satisfies the Schrödinger equation for some Hamiltonian. Okay, so suppose we can map the Hamiltonian to the quantum computer, and we can simulate on the device, and that's actually how Feynman think about that, because he want to map the Hamiltonians of molecules to the quantum devices. Okay, and so suppose there's another thing I want to say. So in this talk, we all talk about this closed quantum system. So there's no noise, and but in reality, so it's in the open system. This open system is in the open environment, and that's actually very important for the real implementation. And so we solve this Schrödinger equation. That's the kinetic part and the potential part, and so we can write this down, this H as the Hamiltonian, and if we write down this using the Dirac notation, we have this. Okay, and this exponential minus IHT is a evolution operator. So Barry Charles, and this is Andrew Charles, and this is also the main player in this field for using quantum computing to solve the differential equations. And so suppose this H is a sparse Hamiltonian. It's a sparse. Okay, so once we discrete, and this is a sparse matrix, and this is acting on MH qubits. It can be simulated within arrow delta, and for this arrow, and also But this looks complicated for now. But you look at this thing, this tau. This is the main thing. This tau, this S is a sparsity, and this is H max norm. Okay. So, for example, if you discretize, for example, a Laplacian equation, and you have 1 over H squared. Okay. If you discretize this equation, you have 1 over H squared here. And that's here. This 1 over H squared will appear here. Okay. And this T, this is a computing time. Okay. And there will be this chorus, and chorus means you want to check what is the entries of this H, and additionally there will be 2 qubit gates. Okay, but this is a unitary process. But most process we interested, for example, Hit equation and other things, And a lot of nonlinear problems and Navier-Stokes, they are not unitary, they are non-unitary process. And how to convert them to the quantum Hamiltonian simulation. Okay. Okay, and that's what Shi Jin and Liu and their postdoc Yu Yue and designed in 2022, and also they developed this formulation for analog quantum simulation. So before that, and we say that is a discrete quantum simulation, but it's also possible to do the analog, so in the continuous space. Okay. Okay, let's say so how to do that. So suppose we have this Heyde equation. It's not a unitary equation. It's not a unitary process because this is dissipated, and with the Dirichlet boundary condition. Jin and Liu, and they introduced this so-called warped phase transformation. That's a simple transformation. So they just multiply exponential minus p to this u. Okay, but it puts this in a higher dimension. Okay, one dimension higher. So that's WTXP. So that's our new equation. So what is the equation satisfied by this W? So you just apply partial t, and you have a Laplace WTXP. But so because there is an exponential minus p, and you can replace this exponential minus p. You just replace this exponential minus p equal to minus partial p exponential minus p. Okay, that's just a simple thing. Okay, but you change this equation. You change this equation into now it's a third order equation. So it has a mixed derivatives. That's the partial t and this Laplace with respect to x. Okay, that's the third order equation. And if you do Fourier transform, you know that the p direction. So all the Fourier modes, they goes from right to left. Okay, so this is a W0XP, and it satisfies the initial condition, but only for p greater than 0, because all the informations go to left. So you can actually extend this initial condition to the left. Okay, so usually we just do this W0XP equal to exponential minus p u0. Okay, so just we put this. Okay, so it decays exponentially on both sides. Okay, and if you do the Fourier, because we can define this equation on the whole domain, so you can do Fourier transform on p. If you do Fourier transform on p, because there's only partial p here, so you have I here, right? You have I eta. Eta is a Fourier transform variable with respect to p, and you have this I eta a Laplacian w hat. Okay. Now, if you regard this if you regard this eta a Laplace as a new operator, and you put I on the left-hand side, that becomes a Schrödinger equation. Okay. So basically, we transform this Heyde equation in Tx domain to a Schrödinger equation on the higher dimension. Okay, so because it's a higher dimension, so we can do quantum computing. Okay, so there is a general formulation. So if you discretize any linear PDE, and you get this kind of thing. Okay, if you discretize any linear PDE, and you get linear ODE, for example. Yeah. Okay, and you can do some augmentation of your system to remove this F. So it becomes a homogeneous system. Okay, you can do some transformation to do that. Okay, so it becomes a homogeneous, and then you can decompose your A tilde into Hermitian and anti-Hermitian H parts. Okay, so this H1 plus I, this is a very simple transformation. And you do this so-called warped phase transformation, so you multiply by exponential minus p, and for the H1 part, you do again this trick, and you have a partial t here. But for this IH2 part, you don't do anything. Okay, so that's good part. And you do the Fourier transform on p, and you get this. Okay, so that's this becomes a Schrödinger equation, because the right-hand side, this h1 eta is a real number, and h1 is a Hermitian, and H2 is also Hermitian. Okay, so all these are Hermitian, and if you write this to like T eta x, and you can write this as a tensor product of tensor product of operators. Okay, and so that's your Hermitian. This is your Hamiltonian. This is your new Hamiltonian, and so this becomes your Schrödinger equation for this augmented system. Okay, so for any linear equation, you can always do that. Okay, so we want to do some analysis for this. There is already this kind of this so-called Nagy dilation theorem. This is in algebra. So if they have a contraction operator, if they, whether or not they can put this into a unitary operator. And this, so what they do is very simple. So they can define this dy. It's a square root because this way has to, the norm of this operator has to be less than 1. This is a contractive operator. Okay. So they define this dy, this square root of I minus v dagger v. But so they can construct this u is like a rotation, right? But in practice, this is okay for construction in algebra, but in practice, this is not easy to calculate. So basically, so most times they do the quantum computing people, they do so-called block encoding, I think, in the next talk, and Matthias will talk about that as well. So suppose, so this is a general method to put arbitrary matrix into a unitary matrix, okay? So let's just think this particular example is exponential minus AT. This A could be a positive matrix, so this defines a dissipative operator. And if this A is positive definite Hermitian, and this can be constructed by, for example, quantum singular value decomposition. This is another technique and very useful. So I will say that it's like the unitary numerical linear algebra. Okay, so this is developed by those people, and we prove that this Schrödingerisation can be also regarded by as a dilation. Okay, so that's one of the dilation. So for this way t is equal to exponential minus at, and we can define this way u as exponential minus I. This is what you say in the Schrödingerisation, right? And you can prove that. So if we project this onto H is the space which this contractive operator is defined, and we get this thing. This is if you work out this Fourier transform, you can get this thing, and each of this is unitary operator. So you can actually do the quadrature. And when you do the quadrature, so it's something like you have the weights here. It's a sum of unitary matrix. Okay, so this exponential minus at can be writing as a sum of unitary matrix, and this is actually the method of linear combination of Hamiltonian simulation developed by Lin and his group. Okay, and well, in the end you get this. Okay. So that's the main part of the proof. Okay. And if we use the theorem which we showed before by Andrew Charles and his collaborators, and we can actually show this optimal gate complexity. This theorem, the number of gates of Schrödingerization is this MD is the discretization on the spatial domain. Okay, suppose you have a d dimension, so each dimension you have m, you have 2 to the power m points, and so you use for each dimension you use m qubits. So in the end, MD is d times m. Okay, and MP is a qubits, additional qubits used by this P register. Okay, because we have this additional dimension, right? Okay, so basically initially, so we have U0, but now because we have this exponential minus P, so we have tensor product states. Okay, this exponential minus P and U0. So now we have this way, and we do Fourier transform for the P register. That's what you say. And now it becomes a Schrödinger equation. So we do the Schrödinger this Hamiltonian simulation. And in the end, we have to transform back. We have to transform back. So we do the inverse Fourier transform. Okay, so we have the WTXP. But for this WTXP, we have to say if this is P is greater than 0, and we keep it. Okay, so we have to measure it. Okay, so if this P is greater than 0, so we measure it and we output this exponential minus P times U. Okay, that's what we get. So in the end, we get U. Okay, and we know that this complexity is only linearly depends on dimension D. And so basically, there is no curse of dimensionality. And that's why we want to develop this. Okay, okay. So now I will just show you how we actually implement it. To just show you some ideas how we actually implement it. Okay. So suppose we use finite difference operator, and this is a difference operator. We can represent this difference operator on the quantum computer, right? How to do that? So that's a simple forward discrete operator, finite difference operator, and this backward finite difference operator. And the important thing is to define this so-called shift operator. This S minus. This is the shift operator. That means if you apply S minus. S minus to some state, you will get J minus 1. Okay, so that definition just means if you apply this to J, and you get J minus 1. Okay, so that's why we call this shift operator. And if you apply this to J, and you get J plus 1. Okay, so this is a shift operator. And so we can define this, we can also incorporate the Dirichlet boundary condition. For example, if we define this operator like this, using this shift operator, and we can get this this operator acting on U. This U is this state defined like this, and defined on U, and we got this state. So for each amplitude, each coefficient is a finite difference. Okay, so that's how we define this difference operator. And so the important thing for the implement on the quantum computer is to use some kind of a tensor product structure. Okay, because this finite difference is easier, so it's easier to implement to use this structure. For example, this shift operator. So originally, if you look at this index, this J from 1 to 2 to the power nx minus 1. But we can express this as a matrix product. And now this index is just J from 1 to nx. Okay, so because we have this and we have efficient implementation. So we just reduce this from 2 to the power nx and to nx. Okay. And once we have this, and we just do the usual thing, and we have the central finite difference with Dirichlet boundary condition, and you do the discretization of this, what we call this Swap transform and Fourier transform, and you get this new equation, finite difference equation, and you can discretize. So that's all you discretize, and so this eta is also discretized. This is a Fourier variable, so you also discretize, and you have the initial condition. This is the way, and you have this tensor product state U0 and P, and when you do the Fourier transform, and you have U0 and the tensor product with E. Okay, and this Fourier transform is this exponential minus abstract value of P, it becomes 2 over eta squared plus 1. Okay, that's just a Fourier transform of this exponential minus P. Okay, so that's just a usual thing, and now you have this Hamiltonian. Now you just write down the whole Hamiltonian. And wow, so that's it looks complicated, but let's just look at this part. So this is J from 1 to nx, and this is a shift of this little shift operator. Okay, this is the decomposition of the whole shift operator. This is the tensor product of matrices. Okay, so that's the important thing here. And so in the D dimension, you still have the similar things. And the time evolution operator. It's just the exponential of this I times this Hamiltonian times tau. Okay, so the important thing is for this H0, you have to know how to implement this, how to realize this exponential I H0 tau on the quantum computer. So basically, how to decompose this as quantum gates, okay, as basic operation. Okay, and well, so I'm not going to say much detail because we use some tricks. It's called Bell basis, and so we can evaluate this U0, approximate this U0 tau is something which you can actually implement it on the quantum computer. So that's something like that. Okay, and so this is W and this is V. So you have something, this controlled operation, this phase operation, Hartmann gate, rotation, and okay, the multiple controlled gates. Okay, so that's all these things and can be realized, at least on the simulator. Okay, yeah. Okay, so that's basically so how to implement this. So you say that if this the numerical method has some structure like finite difference, and we can use that. We can have this matrix product. Okay. And in the end, you have this kind of this similar this circuits, and you can use to simulate your PDE. And well, so we have use these things as a practice for students, and they can, for example, construct for this kind of equations. Okay, so now I will go to the multiscale elliptic equation. So why we can do the multiscale elliptic equation? So suppose we have this equation with scale separation, and the coefficient is like this. So we have n scales, epsilon 1 to epsilon n, and we have strong scale separation. Okay, epsilon k plus 1 over epsilon k is very, very small. Okay, and if you use the usual finite element, and you probably will need a very, very small h. Okay, and so usually people do this two-scale homogenization, and they have this homogenization extension, this U0 and U1. And in another way, and you can define a new variable y. Right? You can define a new variable y, and you have this whole system for x and y. Okay, so that's like you just put your you just lift your dimension from like d to 2d. Okay, so you have this kind of a convergence results. So this is only for U0, and this is for the characters. Okay, and if you have n plus 1 scales, and similarly you can also have this kind of big system. You can get n plus 1 independent variables, x, x1, x up to xn. Okay, so basically you can lift your original problem to a higher dimensional problem. Okay. People don't usually do that because that's the curse of dimensionality. But if you have a good high dimensional method, for example, like tensor method, like Schwab and Oscillatis, and they use this kind of formulation to solve multiscale equations. And for us, so we can, of course, we can use this quantum method to solve all these multiscale equations because it does not care about the dimension. So we have these theorems. So we have some possible quantum advantage. So when the number of scales of dimension is relatively large, okay, compared with classical method. So we have the quantum complexity, we have the classical complexity, but if this the number of scale is larger and all this dimension is larger, so we could have the quantum advantage. And so this is a similar, so estimates, it also holds for parabolic and wave equations. Okay, actually, so I know this work of Daniel, and because in our estimate, we have this condition number inside. So there's 1 over h squared, this condition number inside. But if you can use some precondition and there's no condition number inside, you can actually get quantum advantage for d equal to 1, but with like 3 scales, for example. Okay, so that's probably you can that's something you can try to achieve the quantum advantage. Yeah. So we have some examples, and I will say that in most time we do some of the simulations on the classical computer. There is like a quiz kit and this kind of simulators, which you can put your circuit on this software and you can just simulate. Okay. There's the last thing I want to say is, so most of this method, so the quantum computing method is only works, it works for linear problems. So that's why we say for any linear problem we can use Schrödingerisation to transform this to like a Hamiltonian simulation. But what about, for example, the Hamilton-Jacobi equation? So okay, so this is we have a multiscale Hamilton-Jacobi equation, and yesterday, so we know that, so we can do the homogenization and we can calculate this H hat and to get a homogenized equation, for example, if we want to. But what if we want to solve this on the quantum computer? It's actually there is a clever method by Shi Jin and Liu in 2 years ago, and so they can. So for this is a Hamilton-Jacobi equation. You can find this gradient form. You just take gradient on both sides, okay, and you get a new variable. So this v, okay, v equal to gradient u, du, okay. So you get this new equation. But you can do some transform. You can do some level side transform. Okay, you can do some level side transform to transform this d plus 1 dimensional Hamilton-Jacobi equation into 2d plus 1 linear Liu equation. And Liu equation is like a advection equation, so you can solve this with this Schrödinger equation very easily. Okay, of course, usually you don't do dimension lifting, but for this case, it's worthwhile to do that. Okay, so that and now this u is just the first moment of psi. Okay, this psi is the solution of this Liu equation. Okay, yeah, this is some work we are doing, and in this paper they also discuss this possible quantum advantage for with respect to dimension, with respect to the size of ensemble, because we want to solve the equation with many different initial conditions, and also with desired accuracy for many nonlinear ODEs and PDEs. But in general, it's still very open problem. Okay. So now I want to finish. So we want to have this. Now we want to get this explicit quantum circuits, like just like this. What kind of difference can get you? Okay. And I think Matthias Diamond will talk about something using block encoding, but that's kind of sometimes is a black box. And this precipitation work by Matthias Diamond and Peterson, and I think that's a very nice work. And so you'll say that so originally we don't have quantum advantage until dimension 3, but now probably for dimension equal to 1 we can get some quantum advantage. Okay, and also for time-dependent Hamiltonian. So in this paper, so this because time-dependent Hamiltonian, you have to use the so-called Dyson formula and to find the correlations between so different time. But in this paper, it's also possible to lifting the original problem with higher dimension to time-independent Hamiltonian. Okay, so and also the nonlinear problem. So up to now, I don't know any. So for interesting questions like Navier-Stokes, like molecular dynamics, and also for like nonlinear mechanics, recently Ortiz published, not published, has an archive paper about using quantum computing to do mechanics. Yeah, what can do for mechanics, and but this is quite open area, and what can do and what cannot do. And of course, so this we have to work with physicists and engineers for many problems like initialization, measurement, error correction, and also how to implement on real quantum computers. Because for the simulator you can do anything, but on the real computer there are a lot of constraints. Okay, like the connection of different qubits, like the decoherence time, and you can only allow like 100 of gates or something like that. Okay, so that would be the end of my talk. Thanks a lot.